Welcome to the Human Odyssey, the podcast about human-centered design. The way humans learn, behave, and perform is a science, and having a better understanding of this can help improve your business, your work, and your life. This program is presented by Sophic Synergistics, the experts in human-centered design. So, let's get started on today's Human Odyssey.
Hello and welcome to another episode of the Human Odyssey podcast. I'm Brittany Walton. I'm our strategic operations lead and podcast moderator for today's episode. And with me, I have Jennifer Fogarty here. She's Sophic's Director of Applied Health and Performance. Our topic today is telemedicine and aerospace. This episode is part 2 of our telemedicine topic. In episode 5, we discussed telemedicine in general, and some of our own experiences with telemedicine and some of the challenges and future applications for telemedicine. So if you haven't listened to that episode 5, and you want to hear more on the non-aerospace application of telemedicine, feel free to go listen to that episode as well. Okay, so I want to start off introducing Jennifer and give a little bit of her background for listeners that may not know. Jen actually has an abundance of experience in aerospace. She was NASA's chief scientist for the Human Research Program for many years, so she brings a wealth of experience to this particular topic when we talk about the need for telemedicine in aerospace and the challenges that telemedicine faces just due to the nature of that environment of use. So what is telemedicine in space and what does that mean? So for those that may not be aware, we do have humans living and working in space on the International Space Station, and that's about 250 miles above Earth. So just like us, those astronauts sometimes require remote access to medical care from medical experts here on Earth. So telemedicine allows astronauts to have that remote access to medical professionals that can either walk them through a procedure or conduct a private medical conference with video and audio to help diagnose or treat them in that remote setting. So there's a variety of factors that need to be understood in order to appropriately provide medical care for humans in that remote microgravity setting. We have to understand what the mission profile is. We have to understand what the baseline health is for the individuals going on the mission. So Jen, let's talk a little bit more about the challenges and the opportunities of telemedicine in the aerospace environment. So just to give a specific example, humans actually lose some bone and muscle mass due to the microgravity environment that they're in. So there are certain conditions that are unique to aerospace that we have to consider when talking about telemedicine and the associated hardware and operations needed to occur to provide medical care in space. So Jen, if you can give us a little bit of background on telemedicine and some of your experiences in the past, and what are some of the challenges that have to be overcome when we talk about telemedicine in the aerospace environment.
Sure. Yeah, this has always been, you think historically, so even pre-Apollo, Mercury, Gemini, people trying to characterize what was going to happen to the human body when we took it into these extreme environments and exposed them to forces or lack of forces in the case of microgravity. There was all kinds of conjecture and speculation about what a human body could and could not do, even to the fundamental function of swallowing was a question in microgravity, thinking about if you're upside, the concept of your body thinking it's upside down. It didn't have gravity to tell you where up and down were, how are your tissues going to work. So the remote monitoring is where telemedicine really started, which is instrumenting people with electrodes, some pretty primitive stuff that was available back in the 50s and 60s to mostly detect things like heart rate, ECG, electrocardiogram, looking at how the heart beats, the electrical activity of it, and say, was it regular respiratory rate? And that has evolved over time, as people have lived in space longer. A lot of those missions were very short, especially Mercury, Gemini. They're more like suborbital or orbital for several hours or a few days. But, they needed to get those people back. And of course, there was a lot of robust testing before and after flight. So when we started putting people into space for longer periods of time, now it really became an issue of telemedicine as opposed to just monitoring. Now you have the intent of someone spending a significant portion of their year. And I think you said that was something that was really important, which is there's your baseline health. How is your body going to manifest things over time just because you're and the world at large is learning more about that with molecular medicine, genomics. But then we add a lot of environmental factors that could change the course of your health. And you definitely go through a transition when you go into spaceflight, particularly with the lack of gravity. And of course, people are concerned about other things like space radiation. There's also closed environment. We're not able to keep the atmosphere quite exactly how we have it here on Earth. So, how your metabolism is functioning. So the idea of being able to monitor, diagnose, and treat someone from 250 miles away, and it's even a little more complicated than that because we actually do that on Earth regularly because people have access to resources. So the other part that drives a very sophisticated and kind of on point medical architecture is the idea that these people only have the resources you gave them. So you do a lot of prediction
Right, yeah.
of how and when, if a condition were to occur, and if we were able to diagnose it correctly, do we have the right things to treat you? So I always talk about that as a closed loop system. You had to think through the whole process. The telemedicine part, when you think about it's kind of conceptualizing it here on Earth is like, us being on Zencaster doing a podcast looking at each other. We could be several miles to hundreds to thousands of miles apart. And, it's a pretty seamless interaction. However, typically in the medical domain, you put hands on a patient. You use a stethoscope and you press it against their chest. You use, an otoscope and look in their ear, their eye, down their throat. And you're really touching and looking at the color of tissue, the texture of tissue. You're communicating and looking at the responses a person gives you. Telemedicine allows many of those features in terms of looking, but not the touching. Now you have to have someone be able to articulate more deeply like how they are feeling, or you need more technology to assess them, the way you would normally in an office. So even the concept of listening to someone's heart can now be done remotely using either a dedicated tool. It's called auscultation when you listen to someone's heart using a stethoscope. But what's even more interesting is there are some small adapters that go on things like smartphones that can pick up a heartbeat with enough fidelity and move that signal across in a telemedicine sense so that a doctor actually could listen to your heartbeat remotely. Mm-hmm. And I think, all those tools help us provide healthcare, which and I think, when you mentioned we have periodic medical evaluations for that mere purpose of kind of preventive medicine, how are you feeling? What's going on? Can we look at all your major systems of your body and say, do you look good? And I think for spaceflight, it is always this tension of how much do we need to do those things versus provide other resources. And that could be, other equipment for, say, solar array panels. It's not like it's all about the human. So we are constantly, there's a significant forcing function to be as lean and as light and really austere as possible, but still getting the job done.
Yeah. And that's, challenging when you don't know exactly, what's going to come up, like what issues, might present themselves, especially, thinking forward to, Artemis missions and even more remote extreme environments where, you can't have a launch vehicle there with additional supplies in the matter of, days. And so, how do you understand and plan for, the minimum, viable product to take with you? That's, definitely you have to weigh priorities and, like we said, understand baseline care and, hopefully at some point it'll be more, we'll be more sustained on those extreme environments and, planetary bodies. But, starting off, it's going to be what you brought with you. So.
Yeah. And that is another paradigm shift. So in the concept of telemedicine, and these are just terms that have some implied definitions. It doesn't mean it's still not the right term, but it's a shift in terms of the application of how you do telemedicine. So in the concept of low Earth orbit, even for, government assets like the International Space Station or the future of commercial spaceflight, you have exactly what you described. You have to still, send a lot of things, build this architecture, figure out what you're going to put on the vehicle or in the habitat. Information can be moving between the asset that's in low Earth orbit and the ground and specialist, and you do have a chance to resupply. You have a chance to bring people back pretty quickly. It's a relative measure, but pretty quickly. It is doable. But when you start to move outside of low Earth orbit, even to lunar orbit, lunar planetary, no less a Mars exploration class mission, you're going to need to move from how we do telemedicine, even in that frame, to more like autonomous capability and more automated systems. And all of it, even in low Earth orbit, it really, that prognostic capability of saying what is likely to happen and or be catastrophic enough that we have to build a medical mitigation strategy for it, means it should be data driven. We shouldn't be guessing or talking about how we feel about things, or we have to do the research, we have to gather the data, and we have to be a little creative. We can't always do it in the environment we're going to. We haven't been there yet, so we rely on either low Earth orbit or even Earth based, experiences to talk probabilities, and things more tangible that influence the probability of these contributing factors. Like as if we knew how genetics could affect a reaction to spaceflight and the environmental strategy. We don't quite have that mapping yet, and it is very complex. It may never be actually clear. What you would look for is more of a signal, like a biomarker that tells you when someone might be going down a path. But again, like you have to close the loop in that, and it becomes more and more critical to close the loop in the lunar, whether it be the lunar sorties or the lunar sustained or the Artemis, because to your point, your resources can't be resupplied as easily. You can't get people home as easily. The paradigm has completely shifted. So to give people a sense of order of magnitude, deorbiting a sick person, ill or injured person from the International Space Station can happen within a 24-hour period. The actual function of deorbiting and coming back, which we see during landings, that are captured by the media, even the NASA channels show you from the time that, they undock and then they, enter the atmosphere and you see them, it's on the order of hours. But in terms of, decisions about exactly how carefully you have to get people and the crew in the vehicle and make sure everyone's suited and packed, it's really like a 24-hour process at a minimum to figure out how you can safely land people. Well, in the concept of lunar, that could be anywhere from 7 to 14 days, depending on where you are. It's not a quick event. Mm-hmm. It's much more challenging, which means you still have to have a way to sustain the ill or injured person. So the idea, really, we talk about like the occupational health model, which is engineer out the exposure or the problem, make it as safe as possible for the human so you're not inducing harm. In your baseline health, if you may have changes, because we're keeping you on a mission long enough that your health could change over time. Short missions are a blessing sometimes because we can screen people and kind of rule out a lot of medical conditions that could, appear in 3 to 5 days or 10 days or even 2 weeks. That was a shuttle paradigm. So you can take people who are considered more risky, that have a background of maybe some health issues, and you could be relatively certain very close to launch that you've ruled out the bad thing from happening. It's never zero, but you can get the probabilities down where everyone's comfortable that it's risk appropriate. But when you start going months and years, that's when you really lose control, from a knowledge standpoint. You no longer understand how this person may change over time. And now you got to build in monitoring capability, but also responsive capability that if someone's health were to take a turn, could you mitigate it? So I think that paradigm shift from what we know and kind of conceive as telemedicine today in low Earth orbit is still more challenging in spaceflight than it is on Earth, and in many cases, not in all. But when you move to lunar and deeper space, you have to shift to a medical architecture that's really about autonomy and automation.
Right.
There's also issues with, who will be flying and what will they be capable of, in terms of knowing how to provide medical treatment when they are autonomous.
Yeah, yeah. Before we get to that next section, I just want to take a minute and talk about, humans in space. And telemedicine really isn't a new thing. We've had humans in space for, decades now. And so we've learned a lot. And I would say the other part of, telemedicine, and not just treating and diagnosing people real time, but also, kind of closing the loop and feeding, the research aspect to understand what technologies we need to fill the gaps, that might be there. So your experience, being the NASA Human Research Program chief scientist, I'm sure you've seen a lot of data come through that help to inform industry as well, about, what's needed, what technology gaps do we have. So what's kind of like the number one, you would say, I guess, benefit that we've learned through these, past couple decades, or just something that comes to mind that, has fed back through industry, and we've kind of seen technology advance to be able to treat the need.
Yeah, so the tool that is become most useful in spaceflight, it has the most agility, it's the lightest, the leanest, and it can both be a diagnostic tool as well as a therapeutic tool, is ultrasound. It really has, very early on, I'd say in the International Space Station program, but it actually was toward the tail end of shuttle as well, a very functional tool to do imaging. Now it has its limitations. It can't like get through your skull. Like that's where we've struggled with like imaging the brain, but we've learned a lot, and we've pushed the limits on how ultrasound was used, which actually was a very much an earth-based benefit, whether it be in the orthopedic arena, looking at joints and understanding, well, what does a normal joint with cartilage look like? How does it present itself in an ultrasound scan, which is a learned thing? You say essentially you build these huge catalogs of knowledge and have to screen people and understand, you do it against a gold standard, which might be CT or MRI. We're not going to have computed tomography, which is an X-ray based imaging modality that a lot of people get if they come in with an injury, or an MRI, magnetic resonance imaging. Those are just not practical to put in space. Now, I would say some people are experimenting with MRI, and we have talked about X-ray, but they've never approached the capability and application that we've seen of ultrasound. But it has taken a lot of effort and research over the years to build the knowledge base to support the use of ultrasound, so that you can actually interpret what you're seeing and understanding the range of normal and when it's representing an injury or a pathology, whether it be in a joint. The other area that we really stressed was kidneys, because we have a risk, because you talked about early on in the introduction, when you have disuse atrophy, when astronauts, and there's a little misconception that the level at which their body is transitioning is more like pathologies. And I tend to push back on that a little bit, because it's really disuse atrophy. You stop loading bones, you stop having to carry even your own body weight. So your body's incredibly energy efficient. So it does things like reduces muscle mass. Yes, it's muscle atrophy, but it's not to the degree to which someone can't grow back muscle. Like if you re-stimulate their muscles, or they come back, they can recover. Their bodies, on a cellular level, we're very robust. But to your point, you still need someone very functional during the mission, and the mission may have different needs at different times, especially if you're going from microgravity to a planetary surface. So ultrasound now has been used to look at the thickness of the fibers, within a certain body, a muscle, like the body of the muscle, the thickness of the muscle. You can do estimates of muscle volume. They are looking at ultrasound to do bone density, which is extremely useful to NASA, but it's also useful to people on Earth, because the gold standard is another X-ray based technology. It's called the DEXA, is the acronym for it. And not everybody can get to a DEXA. DEXAs are another big machine you have to lay in and have it be scanned. And you're talking ultrasounds now are literally the size of a smartphone. And so these types of tools, and our spaceflight need to be agile, again, light, lean, it is just really bringing tools that are so deployable no matter where you are. They fit in a backpack and they're part of a suite of tools. So I think I've been most impressed with ultrasound. I'll go back to the kidney for a second. So back to the bone density loss. When you are losing bone density, the calcium has to go somewhere, and your body processes it out, and you're going to urinate it out, which means it goes to your kidneys. And I think most people are familiar with someone who might have had a kidney stone, which most likely is calcium a significant contributor. So crew members were concerned that they're very at risk because they're processing all this calcium out and trying to keep them properly hydrated. So ultrasound now can detect like the earliest symptom of a stone before the person is hurting. And you can do some things like change your urinary acidity, which can stop the crystal growth. And so we can use different countermeasures and do more prevention or early intervention. And now University of Washington has been working on a protocol where you can actually use ultrasound to bust up a kidney stone. Typically, that a technique called lithotripsy was used, and that the lithotripsy was not a practical application in space, but ultrasound using high frequency can also be therapeutic. So ultrasound has been very exciting. And I think the spin back to Earth has really been an incredible tool for places like emergency rooms, remote medicine, and rural medicine.
Right. That's really awesome to kind of see how, the spaceflight environment brings technology, back to Earth, and, we improve on things as we go forward in spaceflight. So switching gears a little bit, let's talk about the wider population of commercial flyers that we're going to see in this new era of commercial aerospace. Especially as you were talking about, having to be more autonomous just due to the more remote nature of those destinations. And when we talk about the commercial industry and, the whole new fleet of flyers that, are slated to go on some of these missions, how do we, and this is kind of where, human-centered design comes into play, how do we ensure that the procedures, the processes, the hardware is usable and functional for people that aren't as experienced, don't have as much training, don't go 3 years of training before these missions, and make sure that, they are able to use what they have to have successful outcomes and successful missions.
Yeah, that's a really, like a loaded issue, not in a bad way. It has a lot of texture to it, because with commercial, you have a lot of people flying who aren't your traditional astronauts the way, a lot of people would think of them. Now, it is true in the case of NASA astronauts and other government, countries who send astronauts, there is a rigorous selection process. And that has a lot to do with these people being thought of as like a long-term career goal. And they are also employees. And there's lots of hazardous exposures in this. So there's an entire paradigm built around kind of picking people who are already very healthy, keeping them very healthy, keeping them very highly trained. So commercial spaceflight being very different than that in terms of you're sending customers who are paying customers. Now, I will say, and to just back this up a little bit, was medicine, particularly space medicine, always considered itself to be enabling. It wasn't about finding flaws in people and saying, oh, you can't go. It was, we're all vulnerable. We all have flaws, no doubt about it, physiologically, medically. But the idea of knowledge could be power, that you knew what to do about it. So there's a lot of work done on the astronaut corps to keep them as healthy as possible. Clearly, they make good decisions, well educated, they live healthy lifestyles. But when it comes to screening and intervention, that is done to really optimize them so they have the lowest risk posture possible. Going back to, if you're going to live 6 months, 1 year in space on an international space station, and we don't have a lot of medical equipment, we're trying to buy down as much risk as possible. But in commercial space, you also want to be enabling, but even to the extreme of sending someone who does have pre-existing health conditions. These aren't people who, these are paying customers, and they want to enjoy their experience in a lot of different ways. They kind of get to determine like how much they want to work versus be a tourist and look at Earth and whatever it is they're going to do. But they may represent medical risks that would be something like, well, in a traditional astronaut sense, that isn't the paradigm, but they're also not going there to work and be up there for months at a time, at least initially. Mm-hmm. But we also, I think at times, have been overly conservative as we've done space medicine, because and this has always been a bit of a conundrum, luck favors the prepared, in that we're not just lucky that we haven't had a medical event. It's designed out to a large extent. We always don't know the molecular level of why bad things didn't happen. We don't have a crystal ball yet, but we definitely have the data that says we're not having medical conditions appear on orbit the way people predicted they might happen. So that's information too. You kind of have to decompose it. You want to know why. But maybe we didn't have to be that conservative in the sense of like government advancement. You're like, well, they're not ready to lighten up, and it makes sense, on our standards and requirements for human health. But on the commercial side, you've got some latitude to start to understand that space of, are these things as hazardous? Like, do they contribute to the probability of a bad outcome as we thought they would? We can actually, and from my experience now, spaceflight, commercial astronauts have very much been willing to participate in human research so they can be characterized, so we really understand their baseline. We watch them, monitor them as closely as possible with a lot of the same tools we do with astronauts, so we have comparable data sets, and say, are the changes they're going through, their adaptation, is that actually putting them on a road to a medical outcome or not? Because both they, the individual, would like to know that. The commercial provider who's taking them would like to know that, I'm sure. And we could prepare better to enable them to still have a very successful experience, even though they have a health condition. So I think it's opening up the door for us to be able to fly more in different people and understand actually some ranges of normal we've never characterized. Going back to the diversity of population has been much different than what the traditional astronaut corps is. Even though that diversity is changing, it changes slowly. Commercial space started out different. So the other element you asked about was the hardware and the human-centered design. And I think that's where a lot can be brought to bear, especially thinking about the future of being autonomous, where you can't put it on the human to be an expert user. That for most stuff, you're going to be sending even the future NASA crews where their jobs are dedicated to other things than being medical providers.
Right.
So that's a similarity with commercial space, that there's mutual benefit there to design things more along the lines of most people are at least familiar with the concept of an external defibrillator, an automated external defibrillator, an AED. That is the type of tool that is in malls. It's in sporting event arenas, places where you have large populations and you might have people with cardiac, issues going on, and the probability, it's just a time and event issue. But if the person goes down, the device has pads that are put on the person that sense and respond to the electrical activity of their heart. And people just have to back out of the way. It's essentially the device is doing all of the work, and it is very safe both for the patient in terms of it would not admit a shock if that were not appropriate. And it doesn't ask the person to get everything just right. There's very kind of primitive directions, not different than what you might get with your iPhone when it says, hello, I'm on, just kind of pictographic things that say, put the pads on the chest in this alignment and turn the green button and step back. And the device actually articulates things to let you know what's going on. So there's some feedback that it's actually doing the job it's intended. So I think most designs for commercial space should use that as inspiration. That's the type of philosophy you would want when you have, especially a medical tool that, given best intentions and someone's thoughts about what might be going on, they need validation, and that should be intra-device capability.
Right. Informing the participant or the patient what's actually happening, is definitely important in a way that they can understand it. So I think the future of commercial spaceflight and government astronauts is really exciting, and I think there's a lot of technology being developed and a lot of foundational activities that are occurring that hopefully we get right, and we make sure that we understand the population that's going to be in these environments using this hardware and make it appropriate for that.
Yeah, appreciate that. And I think there's an opportunity with commercial to have a lot of throughput where you can test and retest, because a lot of it can be sent up. You have you have what you need to support a mission, but then you've got some latitude to do some, we call them, technology demonstrations, and just start to understand, particularly in the paradigm of microgravity, what is going to work and how is still, it has an art element to it. But yeah, I think commercial space is opening up that throughput aspect and also the diversity aspect.
Right, right. Well, thank you so much, Jen. I think this has been a really, really good conversation, and appreciate the insight and expertise that you bring.
I always enjoy talking about medicine and space, and I think sometimes it's a little hard to understand exactly why it matters back to Earth and how it can be applied. And there was a bit more that happened during the pandemic that actually leveraged off of what had gone on to support spaceflight than people realize. But it was really gratifying to watch it be so successful and bring healthcare to people under conditions where they couldn't be seen in person. So I think we're going to keep going down that road. And I really appreciate the opportunity to talk about it and think about some of these things more critically in terms of, where we're having spaceflight, how long the missions are, and who are the people that are going. It's lots of variables to work in there. So lots of opportunity.
Yeah. Right. Telemedicine's not going anywhere as far as the aerospace is concerned. So, well, thank you, Jen, and thank you to our listeners. Thanks for listening to another episode of the Human Odyssey podcast. You can check out our social media platforms for more human-centered content. Thanks, Jen.
Thank you.
The Human Odyssey is presented by Sofix Synergistics, the experts in human-centered design. Find out more at sofixsynergistics.com. Get smart. Get Sofix smart.